Welcome to Chapter 17, Oxygen Sensors. For this chapter, you're going to want to have your textbook available, opened up, and following along with me. So, we left off at this point in lecture right before spring break. We started talking about oxygen sensors. Oxygen sensors come in two forms. They come in narrowband and wideband. In this chapter, we're discussing narrowband oxygen sensors. In the next chapter, we'll take a look at wideband. So first and foremost, what's the purpose of an oxygen sensor? Why do we need one in the first place? So if you take a look back at your old carbureted vehicles, early days, one of the biggest disadvantages was a lack of tunability. The vehicle had no way to adjust its air-fuel ratio on demand. So based on different loads placed on the engine, elevations, air drag, temperature, all these different factors do affect the fuel's ability to atomize. And so we need a way to trim air-fuel ratios. Narrowband oxygen sensors and wideband oxygen sensors allow the computer to have live data, like live actual feedback about how the last fuel delivery was. So the computer is going to reference upstream oxygen sensor data in order to trim out and try to achieve your stoichiometric air-fuel ratio of 14.7 to 1, or possibly a little bit leaner under a cruise situation with low power. And then when we go to full throttle, we go into a mode that's called power enrich with a narrowband. It's a little bit different than the wideband, and we'll talk about that in the next chapter. So if you take a look, first, you guys can read through a lot of this on your own, but I want to dive into, bear with me, the voltage range. Let's go like that. Alright, so voltage range. Your typical upstream oxygen sensor is going to do what's called a switch. So we're switching between rich and lean based off of voltage. Now if you look at the scale here, we've got a 0 and we've got a 1000. This is 0 volts through 1 volt. When the exhaust is on the richer side, you're going to see a voltage reading that's closer to 1 volt. When the exhaust is on the lean side, you're going to see closer to 0 volts. And if you think about how resistance and heat play together, with the increase in temperature, you have a increase in resistance and a larger voltage drop. So it's one way to look at how this circuitry works. So this is all based off of the last combustion stroke, the last power stroke. Oxygen sensors will typically be referred to as like bank 1 and bank 2. And so if we look at your conventional 4-cylinder engine, how many banks do you have? 1. You have 1 bank. On a V-type motor, you'll typically see 2 banks. On your older V-type motors, you'll still see just the whole engine operating on 1 bank. So this is one of the distinguishing factors between older OBD2 technology and newer OBD2 technology is the addition of a second oxygen sensor and a second bank. So now we can fine tune one bank off the other in case, let's say we had a misfire on bank 1. Let's call bank 1 the driver's side. So hypothetically, if we had a misfire on cylinder 1 on bank 1, in the old version, if the entire engine were on 1 bank by itself, all of those fuel trims would be adjusted. So you'd have the driver's side and the passenger side air-fuel ratios being affected, that oxygen sensor data being affected by that misfire. With the addition of a second bank, splitting that engine into 2 sections, we can actually tune one side and try to trim it out a little bit better for that misfire and leave the other side completely alone. And what you're actually seeing is manufacturers are moving closer and closer towards going to the individual cylinder bank. And so there are some prototypes out there, and there are some test engines that I've personally seen where each cylinder is its own bank. And if you think about it, that allows for even finer tunability in the event of a cylinder misfire, or overall elevated emissions might be elevated on that one bank due to that misfire and the consequence of the oxygen sensor seeing a whole bunch of extra oxygen. We can now trim out just the one cylinder that's causing the issue and not affect all the cylinders. So I guess the meat and potatoes of this is the diagnostic stuff. And so what does a normal oxygen sensor look like on a scan tool with data stream? Your upstream oxygen sensor, which is the one before the catalytic converter, is going to be switching ideally between 0 and 1 volts. Now it's not going to actually be 0 to 1. It's going to be closer to 0.2 to 0.8 volts. So remember, lower voltage means lean, higher voltage means rich. So as that vehicle is running down the road, you have constant variance in load and demand on that engine, and so the computer is going to be constantly adding fuel and taking fuel. And so you're going to see that addition of fuel on the upward stroke, and you're going to see the subtraction of fuel on the downward stroke. And you want to see this cycle happening approximately once per second. On an engine that's at a fast idle, or maybe at a light cruise, 2,000-3,000 RPM, cruising down the highway, you'll probably see that cycle, the switch point, happening 3-4 times per second, multiple times per second. So let's take a look at this one over here. What is this sensor doing? Which sensor is this? That is the downstream oxygen sensor, because this component right here is the catalytic converter. And so when we talk about upstream versus downstream, the upstream oxygen sensor, whether it's bank 1 upstream, bank 2 upstream, if upstream is utilized in the description, that means that that sensor is the before catalytic converter sensor. Downstream is referencing the after cat sensor. Downstream oxygen sensors can, but typically don't, affect air-fuel ratio. They do not affect air-fuel trims. There are cases out there, there are vehicles. As a matter of fact, we just worked on one in the lab. It was a Nissan Xterra 2000, 2001, where technically it had the ability, if you read through the circuit descriptions, in the event of an upstream oxygen sensor fault, it would reference the downstream oxygen sensor. So there are cases out there where you have to watch out for, and this is the importance of reading circuit descriptions, component descriptions, because case by case, vehicle by vehicle, manufacturer by manufacturer, they can alter some of this information and how they actually put all these components together. So if an upstream oxygen sensor is supposed to be switching back and forth, what should a downstream oxygen sensor look like? For diagnostic purposes, let's say hypothetically we have a vehicle in the shop with a P0420 code, typical 420 code. 420 codes have to do with a catalytic converter performance issue. And so how does the car know that the cat has a performance issue? You have to stop and think about what it has to go on. What sensors are present in order to monitor a cat? And there's really only one sensor. It's the downstream oxygen sensor. So what happens in most of these computer logic, the code enabling criteria and situations, what's happening is the downstream oxygen sensor is compared to the upstream oxygen sensor. And so the comparison meaning that if the downstream looks like the upstream, the catalytic converter did not do its job. The catalytic converter is supposed to be an inert reactor to mellow out and burn up and convert unwanted emissions into more desirable emissions. Not that emissions at all are desirable, but it's supposed to, let's say, for example, burn off the rest of the unburned hydrocarbons. So let's say the vehicle is running fairly well, and after normal combustion, we have good fuel trims, we have good cycling. Let's say there's 100 parts per million of hydrocarbons left over. What the catalytic converter's job in this case, what its job is to burn off the remainder of those hydrocarbons. And so what's happening inside your engine is you're getting this air fuel ratio fluctuation. Everything up on the high side here, these are rich scenarios. These are lean scenarios. And so you have a little bit too much fuel and you have a lean situation. And in between all of this, you have oxygen. And so that oxygen is going to be available in this catalytic converter through these fluctuations and pulses. You're going to have higher levels of oxygen and then lower levels of oxygen, higher levels of oxygen than lower. And then you're also going to have higher levels of hydrocarbon and then lower levels of hydrocarbons. And so in the catalytic converter, you should have a secondary reaction. And a secondary reaction ideally is going to flatline the downstream oxygen sensor. So in this illustration, you see this kind of switch like this. And in reality, this slow switching signal that they're referencing here, it can look like this, but typically what you're going to see is more of a horizontal line. You're going to see a little bit of movement, maybe cycling between 0.4 millivolts through 0.6 millivolts, and kind of just this little wavy line. Let me draw it on this paper here. So let's say this is your 0 to 1 volt, and this is the downstream oxygen sensor. The upstream switching up and down, right? The upstream's doing this. What you want to see the downstream doing is kind of hovering. It might switch up and then kind of come down and then kind of come up, but it's not going to be switching in that 1, 2, 3, 4 times per second like the upstream oxygen sensor will do. And so when the computer is monitoring this, it's looking, and if it sees a match on the downstream oxygen sensor, it's going to set a code for catalytic converter inefficiency, something to do with that. So we'll talk about catalytic converters specifically when we get into the emissions class later on. Hopefully in May we can be back in school and do that, and we'll get more specific on how to diagnose the catalytic converter itself. But we need to understand that oxygen sensors play a vital role in air fuel ratio, like trimming the engine, but they also play a vital role in emissions component and in self-checking for diagnostic purposes. So part of OBD2 is these emission components have to be able to self-diagnose themselves. And so if you go back to OBD1 vehicles, they did use oxygen sensors, but they did not use, typically, this is in almost all cases, they did not use a downstream oxygen sensor. And so you saw people cutting off catalytic converters, and the car was none the wiser. So OBD2, when that came around, manufacturers were required to put monitoring components on these emission control devices. And so that's why the downstream oxygen sensor is monitoring the CAT. So this is typically what you're going to see in a scan tool, like on a PID. And so if we're talking about how do we actually do the diagnostic check, the book does discuss how to do voltage checks. You can use multimeters, and even better than a multimeter, because the min-max feature is about all you could really see on a multimeter. Even better than that would be to use an oscilloscope. But then again, an oscilloscope, what you're going to see as far as voltage and this fluctuation that we discussed, let me slide this back over. This oscillation in a scan tool is cleaned up. And so what do I mean by that? If you're checking raw data, as illustrated in this picture here, if we're tied into the actual sensor, the image you see is going to be the actual raw voltage, and it's not going to look as clean as the scan tool's interpretation. So when we talk about scan tools lying to you, there are cases where scan tools will clean up an image and kind of give you a little bit of a hard time picking out an issue with a sensor, because they're trying to, I guess, filter that image because you're not going to have clean voltage. You're going to have more of a spiking. And then later in the chapter here, they actually show some illustrations of that. You come over here and take a look. I'm on page 219 now. But if you kind of take a look, this is what I'm talking about. So if we're checking with an actual oscilloscope, we're going to see not as crisp, clean lines. We're going to see more of this hash and more of this these fluctuations. And to the untrained eye, that can look bad. But when you're talking about an oscilloscope versus an actual scan tool, that's the advantage of using the scan tool, is you're going to have a cleaner image. Now, when would you want to use an oscilloscope? If a sensor was marginal. And so, what do I mean by marginal? Let's say hypothetically you had a car that was failing for an oxygen sensor code, performance code. So bank 1, sensor 1, performance. What that code is directing you towards is the oxygen sensor, its switching, its ability to cycle, its image, its voltage is not clean enough or hitting maximum ranges. And so the enabling criteria for the monitor of individual oxygen sensors is going to set up parameters for minimum cycles, for example. You know, how high a voltage it must go to. It might not always go to 0.8, then to 0.2, then 0.8. It might come up to 0.6. It might go down to 0.4. It might not quite make it. So there's certain allowance of lack of performance. Just because the normal design of an engine, you're going to have abnormal combustion events that take place on an engine that's brand new. You're going to have carbon deposits. You're going to have maybe a little bit of junk in the fuel and it doesn't burn quite right. And so there's going to be a little bit of this fluctuation in there that the computer's allowing for. Once you get past a certain threshold in the code enabling criteria, that's where you're going to get a check engine light that comes on. So if you have a vehicle that is marginal, meaning that it's just right there on the edge, it might turn on a check engine light and then the problem can kind of go away. And we typically see that happen on a cold oxygen sensor. It doesn't perform very well. And then as that oxygen sensor warms up, it starts to do its job a little better because oxygen sensors have to be up at an operating temp before they can work. That's part of the open loop versus closed loop scenario. We don't want to start monitoring fuel trims because until the engine's warmed up, we want to stay in open loop. We don't want to go into closed loop until the engine's warmed up because the oxygen sensor is not functioning properly until it's properly warmed up. Just like the cylinder heads have to be warmed up in order to have the fuel atomized correctly. So using an oscilloscope to watch this raw data is beneficial when you're trying to find oxygen sensors that are kind of on the edge. When they're close to failing, maybe they intermittently are failing a monitor, but you can make them look pretty decent on a scan tool. You'd want to look for this type of stuff when we're seeing a whole bunch of up and down cycles not quite making it in the full range. So let's take a look over here. If we think back to what I said, oxygen sensors that are narrowband do not have the ability to see outside of the stoichiometric spectrum. And so the stoichiometric spectrum is your 14.7 to 1 air-fuel ratio, a little bit above and a little bit below. So if 14.7 is ideal, 15 to 1 would be on the lean side, 14 to 1 would be on the rich side. Your narrowband can only see tunnel vision. It cannot see much further out than stoichiometric. And so what happens when we go to full throttle scenarios or zero throttle? We are coming off the interstate and we snap the throttle plate shut. What should the oxygen sensor do in reaction? These two slides are discussing that. So if we look here, we've got this kind of craziness going on. Now, let me move over a little bit. Okay, so we got this little craziness going on, which is normal. This is what I'm talking about, where the scan tool is going to kind of mask some of this weird oscillations that you might think are problems, but they're really not. So we've got an oxygen sensor that's moving, it's moving, and then we go to full throttle. What you're going to see on your scan tool is more of a flat line. On an oscilloscope, you're going to see the actual voltage oscillations. And so when you see the voltage come up, remember, on a narrowband, closer to 1 volt is rich. So what you should see happen on a snap throttle test is the voltage spike upward as high, as closest to 1 volt as possible, and then hang there the entire time you're accelerating. When you go to deaccelerate, you snap the throttle shut. You should see the opposite scenario take place. So why? What is actually happening here, and how does the computer know how much fuel that it's adding? Well, this is one of the disadvantages of a narrowband. It doesn't know. The narrowband oxygen sensor has no idea what the actual air-fuel ratio is above that 1 volt rich point. The computer is programmed from the manufacturer to utilize what's called power enrich. Now, different manufacturers might call it something different, but what power enrich mode is a predetermined algorithm based off of mass airflow sensor data, throttle position angle, map sensor manifold values, engine coolant temp, vehicle speed, all these different inputs, all these sensors. It's pre-programmed that when you go to full throttle, it's going to assume, now that's the issue, it's going to assume that you have a healthy running engine, good spark plugs, good fuel injectors, good air filter, good fuel filter, good fuel pump. It's going to assume all those things are okay, and it's going to adjust the fuel delivery, the pulse width of the fuel injectors, to a predetermined millisecond on time to give the engine what the engineers call for, whatever they came up with for air-fuel ratio for best performance. And so typically you'll see a naturally aspirated engine will be happiest around 12 to 1 air-fuel ratio. So remember, stoichiometric, 14.7, 12 to 1. We're not dropping a whole lot. Boosted engines, your turbochargers, your superchargers, they like to run closer to 10 to 1. Now, there's variances there, compression ratio of the engine, a whole bunch of other factors that come into play, but those are rough numbers. And so what the manufacturer does on a narrowband car, since the oxygen sensor cannot actually see that air-fuel ratio, it's guessing. It's literally guessing as to what the air-fuel ratio is based off of previous engineered dyno tests that they've ran, and then they've pre-programmed into that vehicle. So here's another issue. You can have oxygen sensors working fine in an engine that doesn't run well under wide open throttle due to other issues. So you might actually see this snap up because that's rich, but how rich? Is it 12 to 1 or is it 13 to 1? Is it 13.9 to 1? Does that vehicle start misfiring? Does it start having sputtering because it's got a bad fuel pump or a clogged air filter, or, all those different things? Likewise, you can have a vehicle that runs terrible until you're in wide open throttle. So let's think about that for a second. How can a vehicle run terrible until it's under wide open throttle? Well, if I have an oxygen sensor that's stuck, let's talk about that. What does stuck mean? Go back to my chart, piece of paper. 0 to 1 volt. Let's say I have a lazy oxygen sensor that kind of hovers down, and then it kind of makes its way up, and then it kind of comes back down, and it kind of just lingers. It kind of looks like a downstream. The oxygen sensor data that's sending back to the computer, this should trip code enabling criteria. But let's say it doesn't trip it. Let's say it's 2 drive cycles. And so you have a period of time there where that vehicle is going to be referencing that oxygen sensor data for fuel delivery. Well, let's say, what is this right here? It's 0 volts. Is that rich or lean? If you said lean, you're correct. We're floating on the lean side. So what are the fuel trims going to do in reaction to this? You're going to see fuel trims go positive. So we might see positive 20 on the fuel trim. So short-term fuel trim might be 20. Long-term fuel trim might be plus 10. We have an overall air-fuel ratio addition of 30%. How's that engine going to run? It's going to run terrible. Is it possible that it runs so rich it starts to misfire? Yes. So that customer brings the vehicle into your shop, complaining of a check engine light on, or maybe just complaining of an engine that's running kind of rough. You take it out for a drive, you snap throttle, you go wide open throttle, and it's fine. You go back down to part throttle, and it's bucking, it's spitting, and it doesn't want to drive. It doesn't want to stay on. Maybe it stalls. Depends on how bad it is. So you look at your scan tool data, and you see this upward spike when you go to full throttle. That, in and of itself, is normal. It should go up. Why does the car stop misfiring? Why does the car start to run better? It's because one of those inputs that the computer is referencing for fuel delivery is bad. And in this case, this example, an oxygen sensor, an upstream oxygen sensor that's bad, giving false information, false rich in this scenario, will no longer be affecting the fuel delivery when we go to wide open throttle. The oxygen sensor is taken completely out of the equation because it's not able to see that rich air-fuel ratio that we need under wide open throttle, because the manufacturers have just put a pre-programmed wide open throttle air-fuel ratio in. So there's multiple ways we can go about diagnosing oxygen sensors. This is just an example. Okay, let's take a look at this diagram here. Reference your voltage. Our voltage is 0 to 1. And what we see happening here is normal cycling. Let's say each one of these boxes is 1 second. How many times is this oxygen sensor cycling per second? About 1-2 times. Normal oxygen sensor frequency is from about 1 to about 5 times per second. So this is an example of what you'd want to see on your oscilloscope. Pay attention to one additional detail. What RPM is this at? Might not be able to see it on the camera so well. This is at 2500 RPM. So when I said earlier in this video, you might have a little slower cycle time on an oxygen sensor at idle speed. So typically we want to do these oxygen sensor checks off idle. 2500 RPMs is a good example of that. This is going to simulate running down the highway, running down a local road, much more so than sitting there at idle. Let's move on. Let's talk about hash. What is hash? What are the causes of hash? So, as the book says, hash is the critical indicator of reduced combustion efficiency. What does reduced combustion efficiency mean? What are we talking about there? Combustion efficiency. So let's think about this. We have too much fuel. Are we going to be able to burn all that fuel if we don't have enough oxygen to go with it? That's really what that means. When we say rich scenario, it means we have more fuel than available oxygen. We don't have enough oxygen in order to properly burn all of that fuel. So when we start looking at hash, what we're looking at, and this is the advantage of an oscilloscope here, we're looking for combustion efficiency issues. So what are the causes of hash? Hash on the oxygen sensor signal can be caused by the following, as stated in the book, page 222. Misfiring cylinders, ignition misfires, lean misfires, rich misfires, compression-related misfires, vacuum leaks, and injector imbalances. So let's go through all those. Ignition misfires. Well, that one's pretty straightforward. We have an ignition event that did not take place. In that event, what is going to happen? Can the oxygen sensor see the fuel that did inject into the cylinder? It cannot. What can it see? All the unused oxygen. So momentarily, what's going to happen? You're going to have a momentary increase in oxygen. Lean misfires. What is a lean misfire? Lean misfires are when the air-fuel ratio is so lean that you cannot combust anything. It is possible to have an air-fuel ratio that is so high, so remember, above 14.7 is lean. It is possible to have fuel, but not enough fuel. And that's more on the atom and the molecular structure. When we're causing a combustion event, we're lighting molecule to molecule. Like the flame front is literally expanding and lighting the fuel around it on fire. And so if you don't have enough fuel in that cylinder, you might have a little bit go off, anywhere from a little bit to none, but you're going to have a lean misfire. So what causes a lean misfire? There's a lot of things that can cause a lean misfire. Unlike ignition faults is just there's no spark, right? So how do we have a lean misfire? Does that mean the spark plug didn't go off? Typically not. Typically what a lean misfire is caused by is the lack of fuel in the delivery process. It can be due to an injector itself that's just for a moment got stuck, and maybe it didn't quite open all the way. That might be an intermittent issue. You might have a fuel rail that's partially clogged. You may have low fuel pressure. You may have a fuel filter that's clogged, a fuel pump that's going bad. Lots of things can cause a lean misfire. So when we look at lean misfires and diagnosing lean misfires, we need to think about, is this a cylinder related issue? Is this a bank related issue? Or is it an entire engine related issue? And this is where the value of understanding how individual components, how when they fail, how do they affect the engine as a whole? A spark plug, a coil pack, a single fuel injector, a fault in one of those is typically going to cause one cylinder to go down. A fuel pump, on the other hand, is going to cause an entire engine issue. An oxygen sensor on a vehicle that has two banks, one oxygen sensor going bad is only going to result in one bank having issues. So there's three different kinds of hash. Class 1 hash is amplified and significant hash. Amplified hash is somewhat unimportant hash that is often present between 300 and 600 millivolts on the oxygen sensor waveform. This type of hash is usually not important for diagnosis. That is because amplified hash is created largely as a result of the electrochemical properties of the oxygen sensor itself. Class 2, moderate hash. Moderate hash is defined as spikes shooting downward from the top arc of the waveform as the waveform carves its arc through the rich phase. Moderate hash may or may not be significant to a particular diagnosis. For instance, most vehicles will exhibit more hash as the oxygen sensor waveform is at idle. Additionally, the engine family or the type of oxygen sensor could be important factors when considering the significance of moderate hash on the oxygen sensor waveform. So class 3 severe hash, right here. If you have a vehicle that is exhibiting misfires or running rough situations, this is the important class of hash that you want to pay attention to. So class 1 and class 2, not that big a deal, can be caused by minor little fluctuations in combustion efficiency. It can be caused by normal deficiencies in oxygen sensor components themselves, just inherent design flaws to how oxygen sensors work. But this one right here, class 3. Class 3 hash, this signature cannot be present in any situation other than an engine efficiency scenario. So a misfire issue, such as a fuel pump, fuel filter, clogged air filter, mass airflow sensor, MAP sensor, engine coolant temp, etc. Something that causes the entire engine to have issues, or bank. Compression issues, engine performance, and like mechanical integrity issues will also result in a hash that looks like this waveform here. So if we talk about, when I go back to find a piece of paper here, I talked about what scan tools can do. And the importance of scan tools and knowing this, scan tools will tend to take that hash and clean it up. And so when we're looking at raw waveform data coming out of an oxygen sensor on an oscilloscope, and we're seeing this as opposed to that, we want to pay very close attention. Would a scan tool show you hash, it might show you some, but it's typically going to clean that image up. And so when we're looking at diagnosing drivability issues on a car via the oxygen sensor, we need to understand that the scan tool data can lie. Typically, the scan tool data is enough to go on because we're going to see a scale range. So let's say we have a vehicle that's running with a lack of fuel. So it's misfiring and we have lean misfire situations taking place. What is our waveform going to look like? So when we got a 0 to 1 volt scale, what is that waveform going to look like? We're running with a lean misfire, a lack of fuel. What you're going to see is not a rich scenario, but you're going to see a lean scenario. And so in a case like this is part of the reason why I say scan tool data is still good, and I still like to use scan tool data. What you're going to see here on the 0 to 1 volt scale, remember, this is the rich side, this is the lean side. What you're going to see is a voltage range that's kind of doing this, cycling up and down, but not making it to the full rich, hovering down at the lean side. You might see the occasional point where we make it up to 1 and then come back down, then hover down low again. Where this scan tool data, this is actually showing on the richer side. It's kind of the opposite of what I just said, but you could also notice, though, my point is that it's not making it all the way down to lean in this example. And so it's kind of just hovering. So what the scan tool is going to do is going to clean that up. It's going to look a little bit crisper. You're not going to quite see all that hash, but you're still going to see the overall oxygen sensor switch point hovering. In this case, this straight line is your 4.5. Excuse me, your 0.45 millivolts, your 14.5 to 1. This is your stoichiometric right here. You're seeing this air-fuel ratio still hover on the rich side on this example. If you saw that hovering on your scan tool more on the lean side, whether or not you could see the hash, if the scan tool is cleaning that up, you're still going to see that overall waveform cycling one side of the scale or the other. You can't have a misfire situation take place where you're cycling the full range. If you think about what's happening there, you have misfire, you have oxygen, too much oxygen left over, or maybe you have an air filter issue and you have a restriction of oxygen, which is probably the case of this one here. Lack of oxygen, so you have too much fuel, not enough air. You're misfiring because you're so rich, you're hovering on the rich side in this example here.